In this screencast, we'll talk about some asymptotics of synthetic division. So we talked about synthetic division of polynomials in several previous screencasts. So we have the nth degree polynomial Pn of x equal to an times x to the n minus 1, x to the n minus 1, like all the way down to a0 times x to the 0. And the synthetic division of polynomials is the process of dividing the nth degree polynomial by the linear monomial x minus b. And we discovered, that's the third discovery that we made, that when Pn of x is evaluated at b with Horner's rule. You can watch the previous screencasts in this channel to find out how that is done. The coefficients of synthetic division are computed as byproduct. Well, can be computed as byproduct. We can just keep track of the iterative values of the polynomial the nth degree polynomial that we're evaluating at b with Horner's rule, and they turn out to be the coefficients of synthetic division of that polynomial by the factor x minus b. And the question for this screencast is synthetic division any faster asymptotically than regular long division? Because we can naturally ask, well, why do we need synthetic division? Well, why not do just regular long division? Can we do any better, or are we better off with synthetic division, right? So let's iterate through a couple of examples of long division. So let's say we have the first degree polynomial a1x plus a0, and we will divide that polynomial by the linear monomial x minus b. So the first factor is a1, obviously, so the first coefficient, if you will, and here we have a1 times x minus a1b, and so we subtract this a1x minus a1b from a1x plus a0, and we get a0 plus a1 b. Since the x factors are out, we're out of the x factors, the division is over. So the result will be a1 plus a0 plus a1b over x minus b. So the sequence of coefficients to represent the result of this long division is a1 and then a0 plus a1b. Okay, so let's do the second degree polynomial, right? The generic long division for the second degree polynomial, right? Dividing the second degree polynomial by the x minus b monomial. All right. So we have a2 x2 plus a1x plus a0 divided by x minus b. So we get okay, the first factor is a2x. So a2x multiplying it by x minus b, we get a2x squared minus, let's see what we get, a2bx, right? Minus a2bx. Okay, let's write it out. Minus a2bx. Okay, now let's subtract that, and from a2x squared plus a1x plus a0, and we get a1 plus a2bx plus a0. Right? Okay, plus a0. Okay. Then the second factor is a1 plus a2b, because we are going to get rid of a1 plus a2bx. So we are going to multiply a1 plus a2b by x minus b, and we get a1 plus a2b times x minus a1 plus a2b times b. Right? B. Okay, I'm running out of space here, and this is times b. Okay, b. It's barely seen, but it's going to be seen after we're going to do the subtraction. So we're going to get a1 plus a2bx will cancel out, and or subtracted, will be subtracted out, and we're going to get a2 plus a1 plus a2b times b. So the sequence of coefficients for the result of this long division, or doing synthetic division through long division, is a2 plus a1 plus a2b plus a0 plus a1 plus a2b times b. Right. So this is the final factor at which we stop. So the answer is a2x plus a1 plus a2b plus a0 plus a1 plus a2b times b over x minus b. So the result of dividing the second degree polynomial by the linear monomial x minus b. Okay, so I'm running out of space here. Let me erase this and make sure that this is a1, right? This is a1. Okay, I'm running out of space here. So, but let me just state the result of let's do the third degree polynomial and divide it by the linear monomial x minus b. So a3 times x cubed plus a2 times x squared plus a1 times x plus a0 divided by x minus b. So you can pause this screencast and see which coefficients you're going to get as a result. So I get a3, then a2 plus a3b, and then a1 plus a2 plus a3b times b, and then a0 plus a1 plus a2 plus a3b times b, right? So this is a3x squared plus a2 plus a3bx plus a1 plus a2 plus a3b times b, and then a0 plus a1 plus a2 plus a3b times b over x minus b. So we're ready for the pseudocode for long division, or doing synthetic division through long division. So we have the usual array of coefficients a(n) through a0 to represent our nth degree polynomial. Then and this is our input, and then on the input we're going to get b, which is the factor in the linear monomial x minus b, and we need the current coefficient, which is initially set to an, right, the first element in of the coefs. Right, and then for I from 1 up to n, we're going to iterate through the remainder of the coefs, and the current coefficient is set to the ith coefficient plus the current coefficient times b. So a3, this is the first coefficient, then the next coefficient is a2 plus the current coefficient a3 times b, and then a1 plus the current coefficient times b, which is a2 plus a3 b times b. So eventually we're gonna so this is basically a sequence of coefficients, and we need to keep track of those coefficients that represent the division, right? The long division of the nth degree polynomial by the linear monomial x minus b, and obviously we need to keep track to collect those current coefficients. So let's say that we have this array div coefs, and we append the current coefficient at the end. Right, so we have this function append. Alright, and at the end we return the div coefs. Okay, so how fast is this? Well, obviously this is a linear algorithm, so we have theta n. So let's assume that the length of the coefs array is n. So we have theta n multiplications and theta n additions. So it turns out that the long division is the same, has the same speed asymptotically as the synthetic division, right? So which is somewhat surprising, because one would think that we have to push so many symbols in the sheet of paper when we do long division, but nonetheless it's as if implemented correctly, it's as efficient asymptotically as synthetic division, right? So we can do synthetic division through long division and be in the same asymptotic class. Okay, so let's go and take a look at the Python source code that implements long division, that does synthetic division. Okay, so we have the coefs. That's the array, and the ith coefficient a sub I is the ith coefficient of the nth degree polynomial. B is the constant in the linear factor x minus b. Well, linear. Let's call it linear monomial. And then div coefs are the coefficients that represent the division of the nth degree polynomial by the linear monomial. So this function, synthetic division through Horner's rule that we implemented in the previous screencast. So we're not going to talk about this, but the next function is the iterative implementation of the long division, the synthetic division. For synthetic division, so we have coefs, we have b, we have the current coef, which is the initially set to the nth coefficient, and then we just compute the current coefficients and put them into the array div coefs and return div coefs as we did in the pseudocode. And this is another implementation of long division that does synthetic division, but this implementation is sort of this Lisp style recursive implementation. And at the end of this file below we have several tests just to make sure that our implementation works properly, and it does work properly on these examples, and all these examples. And we get three arrays. The first array is SPD coefs, is done by applying our synthetic division implementation. Then the second array is LSPD coefs, that's the long division, and then the third array, LSPD rec coefs, which is the long division, the recursive implementation of the long division to do synthetic division. So this is the output. And it appears to be right, so it appears to be correct. So these are the three arrays. So SPD coefs, LSPD coefs, LSPD rec coefs, and then there's a couple of assertions to make sure that the arrays are the same. So all these three functions must return the same array. Well, equal arrays, not the same array, but equal.